So this is the test number 4 review. And if you've done, most of the homework, or all of the homework in sections 4 and 5, you should be in really good shape, and you've worked the stuff in class. So there are a couple of simple integrals, both definite and indefinite integrals, that just involve some polynomial. So I'm just going to make one up here. So, in this case, we don't need to use U substitution. We just have individual terms of a polynomial. So you would use the power rule formula, and that's kind of, let me see, really there's only a few things you need to know for this test as far as writing down your cheat sheet. Is you need to know that the derivative with respect to x of x to the n is equal to n times x to the n minus 1. And you use that to find du, basically. There's also the derivative with respect to x, the sine of x is the cosine of x. The derivative with respect to x of the cosine is negative the sine, which we derived all these in chapter 2 using the limit definition. And then consequently the integral results are the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus arbitrary constant c. The integral of the sine of x dx is equal to negative the cosine of x, and the integral of the cosine of x dx is the sine of x dx. Okay. Okay. So those are really the only 6 equations to use. So in this case, we would just use this result here, x to the n. I guess there is one more that we could kind of use. The integral of k times f of x dx is equal to k times the integral of f of x dx. So if you have a constant, you can bring that outside the integral sign. So in this case, you have the constant of 4, and then you'd multiply by the integral of x to the 4th, which would be x to the 5th over 5. Then you would have the constant 3 multiplied by the integral of x squared, which is x cubed over 3. The integral of a constant is just a constant times x. And then we add arbitrary constant c. Now, if we had a definite integral, we wouldn't have to change the variables on the integration. If I were to put 1 and 3 on there instead, what you would have in that case is you would have the same result here. You wouldn't have your arbitrary constant c, and you wouldn't have to change the variables. So in the case of just a straight polynomial, there's no U substitution that needs to be done. You just have to, we get so used to U substitution that we forget that there are some simple integrals that we can do. We don't need to use U substitution. So just be careful about that when you get to that point. Okay. And then there are going to be a series of different functions. For example, like 7x divided by the square root of 3x squared plus 5 dx. Okay, obviously this doesn't fit any of the simple ones, so we need to get into this form, and unless it involves a trig function, it's going to be this power rule function. So we need to rewrite this as the integral of u to the n, basically. We're going to use U substitution. And, today we learned about the natural log, and that's the case where if you have something over not a square root or a power, you choose u to be whatever's in the denominator. But in all these cases, if I had this, or if I had this, like same u's. If I had something like 7x times the sine of 3x squared plus 5 dx, or if I had 7x times 3x squared plus 5 to the 7th power dx, or I had, what else? Other options are there? It could be 7x divided by 3x squared plus 5 to the 4th power dx. Okay, so these are all variations of the term. The u term is going to be whatever's the argument of the trig function, the argument in the square root, all the stuff that's in parentheses. So in all of these cases, u is going to be equal to 3x squared plus 5. And as a consequence, du is going to be 6x dx. The derivative of 3x squared is 3 times 2, and reduce x by 1, multiplied by dx. So in all of these cases, though, what we would do first is we would factor out the 7. You don't have to do this, but, I think it's good to get in that habit, so we do the same thing every time. But, we're just going to factor out. Okay, same here. Factor out the 7, whatever the constant is. And likewise here, 7. And we do that just so we get x dx in all cases. Okay, so there's our u and our du. And notice I have x dx in all the cases. I forgot the dx here. So I have x dx. So I want to solve this for x dx. So you just take the du term and you divide by whatever constant that is. Like that. So what I'm going to do is I'm going to move this over here, and then I'm going to write all of the different results I'd have. So then I could rewrite this as 7 times the integral of 1 over the square root of u times du over 6. This one I could rewrite as 7 times the integral of the sine of u times du over 6. This one I could write as 7 times the integral of u to the 7th du divided by 6. And this one would be 7 times the integral of 1 over u to the 4th times du divided by 6. Now, before I integrate it, in each case, I'm going to so what I can do is I can take, the 6 in the denominator here, and I do this in a separate step, but I'm going to do it. In each case, I could factor out whatever that constant is that's in the denominator. And now what you see is I've got all of these can be rewritten as a power expression. This one's going to be u to the negative 1/2 power du. This one, we don't, this is actually the sign. Here we're going to have 7/6, the integral of, well, we don't have to change anything there because it's already in the form. And this one we would have u to the minus 4 power. So anything that's in the denominator here or here, you have to rewrite as an exponent that's in the numerator. So this is u to the 1/2, and you move to the numerator, and you get u to the negative 1/2. Here it's 1 over u to the 4th is the same as u to the negative 4. So then all you have to do is you just have to integrate using this formula in terms of u. And then once you've done that in terms of u, then you can substitute back in. So again, I think if you've been keeping up with the homework, then I'm not going to go into any more detail with that. There are these cases where you think you might have to use u substitution, but you don't, and we kind of had that when we did the derivatives. We had a case. So I'm going to just give you an example, and you can be on watch out for this. So, let's say I had the integral of 4x squared plus 2x plus 1 divided by the square root of x dx. And you might think, oh, I need to use u substitution. But, if I let u equal x, that doesn't do me any good. If I let u equal this whole thing, the derivative of this is nothing close to that. So if that doesn't work, then you might say, well, maybe I can rewrite this as 3 terms, because I've got the same denominator in all 3. I've got the same denominator because it's this whole thing divided by that. So what you would end up with is you could divide each one of these by the square root of x. So you'd have x, and dividing by the square root of x, remember this is x to the 1/2 power, so then you would subtract the exponents. So you'd have 2 minus 1/2, and then you would have 2 times x to the 1st power minus 1/2, because that's from the square root, and then you have 1 times x to the negative 1/2 power. So I'm just converting all of these, converting this to a fractional exponent, and I'm subtracting the exponent here is 0, x to the 0 power. So once you do that, you can simplify them. You get 4x to the 3/2 plus 2x to the 1/2 plus x to the minus 1/2 power dx. And so this is basically like the first case here, except the 3 terms don't involve whole number exponents. They involve fractional exponents. But then you can integrate it. You add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add your arbitrary constant c, and then you can simplify that. Remember, when you have these fractions, you want to multiply by the reciprocal. So you'd have 4 times 2/5, 2 times 2/3, and then the reciprocal 1/2 would be 2. So I'm not going to work that out. Now, there's one problem where I actually ask you to solve this differential equation. There's really nothing that exciting about it. So I'll give you, instead of saying, find the integral of this, I'll give you this differential equation. So let's say it's 5 minus 4x squared. So that's my differential equation. So I give you dy dx, and I ask you to find what is y. So when you see this, what you want to do, and I also have to give you some initial conditions. So I'll say y of 2 is equal to 15. Say that's my initial condition. Or, it doesn't have to be at t equals 0 or at x equals 0. It can be at any value of x. So this is my x value. This is my y value. And I'll need that when I want to get the particular solution. I can do the general solution without knowing this, but to get the particular solution. So what we do is we multiply both sides of the equation by dx. And then we integrate both sides. And you see on the right-hand side, I just have a simple polynomial, so don't have to use u substitution. And on the left side, the integral of the differential is just the function. That's what I'm trying to solve for. That's y. So then I just use the integral of x to the n dx is x to the n plus 1 over n plus 1. So in this case, the integral of 5 is just 5x. The integral of negative 4x squared is negative 4 times x cubed over 3. And in this case, I'm doing just an indefinite integral in this case, so I add my arbitrary constant c. Okay, so that's my general solution. Then I can use this as my initial condition. So this is the y value, and this is the x value. So I take the general solution, I move this, and this is where people get these mixed up. You want to make y equal to 15, and you want to plug in whatever's in the parentheses. And the only unknown is, once you apply the initial conditions, is the arbitrary constant c. So we go ahead and multiply all this stuff out. So 2 cubed is 8. 8 times 4 is 32, so I get 42 thirds. And then I'm going to solve for c, so I'm going to subtract 10, and I'm going to add 32 thirds. So subtract 10, I'll get 5, and then I'm going to add back in 32 thirds, and that's going to equal c. And I have to find a common denominator, which is 3, so that'll become 5 will become 15 thirds. I'll add that to 32 thirds. So c is equal to 47 thirds. Okay, so my final answer that I want is not just figuring out what c is. I need to plug that back in. So I get 5x minus 4x cubed over 3 plus 47 over 3. And what should happen is if I plug in 2 here, I should get 15. Now you don't have to do that, but I'm just going to prove that it's true, that I did it correctly. So you'll get 5 times 2 minus 4 times 2 cubed over 3 plus 47 over 3. So that's 10 minus 32 thirds plus 47 thirds. Okay, sorry for the pause there. I had to stop, and for some reason my headphones didn't turn back on. Okay, so anyway, we're finishing this thing off. So you get 10 minus, you get actually plus 15 thirds, because 47 minus 32 is 15. 15 thirds is 5. So you get 10 plus 5 is 15, which is the answer. So that's how it works. Okay, so there's going to be a problem like that. There's this second kind of U substitution type problem, and that's where you have the square root of something here, and maybe something like that. And I actually tell you use the second type of U substitution. So when you have this situation, if you try to let this be u, then du would not match up. So you have to just know it's going to be the square root of just a linear type term, and then the outside part is going to be some kind of linear thing as well. It doesn't actually have to be linear, but this part has to be linear, and if you take the derivative of that, you're just going to get negative dx, so it doesn't really help you any. So in this case, you still let u equal determine the square root, and in this case, du is just simply negative dx. The derivative of negative x is negative 1. Negative 1 times dx is negative dx. So that's du. But what you need to do is you need to write x in terms of u from this expression. So we do one extra step. And in this case, we'd say x is equal to 2 minus u. How do we do that? Because if I take this negative x, move it over here, and then take u, move it over there, this u becomes negative, x becomes positive, and you get 2 minus u. So then all you have to do is substitute in for both x and 2 minus x. So x becomes 2 minus u times the square root of u times negative du. Don't forget the negative sign if this is negative x. If it's positive x, this is going to be positive. It's going to be positive du. Now at that point, we could factor out to 2. And then if you multiply, you want to multiply this out, so you'll get 2 times u, the square root of u, minus u times the square root of u, which is u to 3/2 power. And that whole thing here is times d, negative du. So let's go ahead and factor out the negative sign. So this negative that comes out here, this 2 comes out. And then you can, this is just a simple 2-term polynomial, so you just apply the, this is u to the 1/2 power. So you get negative 2 times 2, which is 4, u to the positive 3/2. 1/2 plus 1 is 3/2, divided by the new exponent. The second term, you're going to have negative times the negative, so it's going to be positive 2. And then you integrate u to the 3/2, becomes u to the 5/2, divided by the new exponent. Add your arbitrary constant c. And then you can take the reciprocal of 3/2, which is 2/3. 2/3 times 4 is 8/3. You get 8/3 u to the 3/2. Here we get the reciprocal of 5/2 is 2/5. So 2/5 times 2 is 4/5. U to the 5/2 plus c. And finally, you have to plug back u into it. So you go back here, you know, like, what was u? 2 minus x. So I'll get negative 8/3 times 2 minus u to the 3/2 plus 4/5. 2 minus u to the 5/2 plus c. Now, if, oh, that should be x. I don't know why I did u. So this is x. Now that's, you don't have to simplify anything beyond that. Now, let's just, I give you one like this, which is an indefinite integral. There's also a definite integral, so you make sure you know how to do this both ways. So let's say I had, 4 and 7 for the same problem. So the only difference between the indefinite integral and the definite integral is I would redefine my limits. So when x equals 4, u is equal to 2 minus x, or 2 minus 4, which is negative 2, and then the upper limit is 7, u is equal to 2 minus 7, which is equal to negative 5. So when I get down to this substitution part, I'm going to change the limits from 4 to negative 2 and from 7 to negative 5. And then I have negative 2 times, this part right here, or actually this part right here. So, and then the rest of it, it's the same, except when I get down to here, when I do the integral, instead of adding the arbitrary constant c, I'm not going to add the arbitrary constant c, and I'm also not going to substitute back in for u, because I already redefined my limits. And so then I can plug in u equals negative 2 and u equals negative 5, instead of plugging it back in and then doing x equals 4 and x equals 7. It just saves you one step of having to plug back in. So that's the basic difference between the definite integrals and the indefinite integrals. So there are 12 problems on the test, and 8 of them are indefinite integral type things, and there are 4 that are definite integral type problems. So the key thing is you're still using u substitution. You've got, for the definite integrals, you want to do this part where you redefine the limits of integration, change the variable, do all the integration with respect to u, and then evaluate the limits at the u limits, and that'll give you the answer. You could also, change it back to x and do the x limits, and you get the same answer. Just one less step that you have to do. So that's all I'm going to say for right now. So do make sure you know how to do these. We didn't do a huge amount of it in class, but there was some homework assignments that you had to do. So kind of in review here, let's go back. I'm going to give you two problems just involve simple polynomials. You don't have to use U substitution. There's going to be probably 6 or 7 that involve U substitution, both definite and indefinite integrals. It should be pretty obvious what you're substituting for U. So I showed you all these different possibilities, and you'll get different possibilities like this. There will be one problem where you have to just simplify this kind of expression and then do the integration. You don't have to use U substitution because the things we're integrating are just x to the n. Sometimes people try to use U substitution here and get all screwed up. There'll be a differential equation, which will be just simple using integral of x to the n dx. You just have to know how to use the initial conditions. There'll be two problems that use this other kind of U substitution. One is an indefinite integral, one that's a definite integral. They always end up with these fractional exponents like this. If you're dealing with the indefinite integral, you need to substitute U back in. But if you're dealing with the definite integral, then you need to redefine the limits and plug those in. Once you integrate with respect to U, just evaluate it at U. And again, all the definite integrals are just going to be like the indefinite integrals, except you need to have limits converted to U. If that's there's one that's just a polynomial, so you won't have to do the U substitution. But 2 of them you will, like the ones that we showed earlier, and then there'll be one that involves this second type of U substitution. It's really nothing tricky. Most people do pretty well on this test.